Hey everybody, we're going to go ahead and do question 23 here in the notes, just giving you another example of a harder rational function to deal with and to take apart and to end up graphing. So the first thing I look at here for r of x, it's x squared minus 2x minus 8 in our numerator, and that's divided by x minus 3. And I think it's easy to maybe start by taking things apart, seeing if we have pieces that potentially cancel, and so that would mean we need to x factor the top. Okay, factoring it out puts negative 8 in the top of the x factor and negative 2 down below, and negative 4, positive 2 are the two numbers that multiply correctly and then add correctly. So I can take that information and put it right back together here. So in my fraction I have the groups x minus 4 and x plus 2, and that's over x minus 3. And I was hoping for perhaps groups that would cancel, but the fact that I know nothing cancels tells me some important information. It tells me that I have no holes in my graph, which is a good thing, that I don't have to worry about potentially falling in a hole. All my points are going to be solid points. So the second thing I look at is from the numerator and the x-intercepts that the graph should have. And so that's going to happen from the top information. I'm going to have x equals 4, so 4 comma 0, and I'm going to have x equals negative 2 comma 0. So whatever makes those groups 0 is where your x-intercepts would be. We can mark those on our picture, because I know my graph is going to be anchored at those locations. Excuse me. Then the third item that I like to look for is vertical asymptotes. The bottom of our fraction determines those, and so I'm going to have a vertical asymptote at x equals 3. That is a restriction that I would not want to use. That would be dividing by 0 on the bottom. So here we go. After I get my asymptote drawn in on the graph, the last part is figuring out where the horizontal asymptote would be. I think that's trickiest. That's the thing that I taught you last through this section, because you have several different options. For this particular problem, back in the original r of x question, we had a quadratic over a line. And so this is a problem that is a bigger degree over a smaller degree. And whenever you have big over small, I would encourage you guys to do long division just to reveal structure. Same over same, big over small, long division typically will help reveal a few things. But before I get to that, let's go ahead and let's talk about how we can view this. Ultimately, the 2x and the 8 in the top don't matter when you get very, very, very large. X squared has so much more power over where the graph goes. Same thing on the bottom, the minus 3 when you're in the billions, minus 3 is like hardly anything at all, hardly any impact. And so it's only the leading terms that matter when x gets extreme. So this will end up resulting as x goes to positive or negative infinity. It'll act like x squared over x. And if you reduce that down, that is equal to x itself. And so actually what I'm seeing here is that we are going to have probably a slanted asymptote, an asymptote that acts like a line, and that's because we're not equal to a number, or we're not equal to 0, we're equal to something that changes and something that varies. So in this question, I want to hold off for a minute before I write y equals, whatever my equation will be for the horizontal asymptote, because long division really is a good thing to try. X minus 3 is what we are using as our divisor. X squared minus 2x minus 8. You hope this process doesn't take too long, but here we go. X times x, I believe, creates x squared. X times negative 3 underneath makes negative 3x. Then we take those two things and we subtract both of them away, so distributing the negative essentially. We get 0. We should always get 0 there. And then negative 2 subtracting negative 3, that's adding 3x to end up with 1x, bring down negative 8. So this is still possible. I can multiply x to get 1x. It just takes 1. And this is actually kind of interesting. The difference between just doing the simple estimate and doing the rigorous division, I can see that x plus 1 is actually going to be the equation of this line. This is the asymptote part of my problem. Okay, but we need to finish our division. So 1 times x is x, right below here. 1 times minus 3 is minus 3. And then I go ahead and I subtract those things away, getting 0. And negative 8, subtracting negative 3 is negative 5. There is no way to multiply an x to get a constant, so we are done when your divisor's degree is larger than what's left over. Writing this remainder, we should be able to put that back up here in a fraction, so plus negative 5, and then that is over x minus 3. And typically your answer for long division is all scrambled up. It might be beneficial to write the rational part first, so your fractional remainder, negative 5 over x minus 3, tells me I have a reflection, tells me I have a stretch. And those things are going to fit with an asymptote that is x plus 1. Knowing that the leftovers here at the end, or what you get first in long division, is your horizontal asymptote is a big deal. Okay? You can actually get x squareds and x cubes. You can get different shaped asymptotes, and then the rational kind of fits on top of whatever that shape would be. But we don't typically do anything that crazy. X squared plus 1 has a slope of 1 over 1. That's what the 1 in front of the x does. And the y-intercept is going to be at 1, the b value. So if we take those ideas and we put them on a graph, 1 is going to be where it starts, and then up 1, up 1, up 1 and over 1, up 1 and over 1, up 1 and over 1. This graph is going to travel along this diagonal, and you can see this point to the left is already kind of close to where we'd expect it to be traveling. So let me make this dashed. It's always good to make asymptotes dashed because, you know, they don't really fit on the graph as solid lines. It's not really there, it's invisible. So now we can go ahead. It's probably advantageous to do an XY table. Okay, I'm just not seeing anything else I can get information from, and so an XY table I think is our best route. So we'll go ahead and we'll set that up, and this is where we would probably just use a calculator. Okay, typing that into our calculator under the y equals menu. You can type in the grouped form, so I think that's maybe the easiest. If we have an x minus 4 next to an x plus 2, we double parentheses because we're trapping all of that together, and you just divide it by the x minus 3 group. I could have done the original quadratic over the line. It's the same idea, but I just thought I'd give the second option a shot. You can see it's traveling along that asymptote, then it starts to increase. The vertical line through the middle of this graph is just a byproduct that my calculator is not very good. It's not supposed to be there. It tries to connect the maximum values in its computer brain to its minimum values in its computer brain, and it thinks they're all connected in one curve, which isn't true. This graph's split in half, but then it travels upwards and then starts to get close to the asymptote again. So how do we get those points? Well, going to the table, and then kind of asking for different points. Like I have -2, and using -2 in here confirms that I get 0 out of this. I also have 4. 4 comma 0 is actually this bottom point. But some other points that might be of interest, 0 and then 2.66666, so that would be our y-intercept, 2.6 repeating. So that's roughly right around here. Good to know. Maybe a value around 2 would be good because that's a little closer to our asymptote, and so I can put 2 in. That gets a value of 8. Oh, that was really big. Then I can choose some values that are a little bit to the right of the asymptote, the vertical asymptote, so maybe 3.5. That's negative 5.5. I probably want to write down that 2,8 point as well that I put in my calculator. And then let's get one over closer to like maybe 9 or 10 or somewhere along those lines. 9.16. So 9, 9.16. Roughly here, which yeah, is starting to graze or get closer to that asymptote. So it takes a little bit of practice, but you can hopefully draw kind of a curve that goes through some of those locations. Same thing over here, very close to the asymptote, curving through some of these points, and then starting to travel upwards, because again, you cannot cross x equals 3. It is uncrossable. Vertical asymptotes cannot be crossed. So our domain, our x values, would be all reals. Okay, and there is one x value as I travel across that is not used. Happens here at 3. There is a void at that x value along the whole graph. So x cannot equal 3. That's from dividing by 3. You never want to do that. Or dividing by 0, excuse me. The range. This is where things get a little weird. Okay, if you look along the graph in a vertical direction, this graph actually covers all reals, and there's never a gap, there's never a point in this picture where I have an absence of heights. In fact, as I draw across this at heights of negative 3.5, negative 1.5, 0, almost 3, 5, I hit the graph in multiple places. And so downwards and upwards, and no holes or gaps in that direction, is a range of all real numbers. There isn't any restrictions on this particular rational function. Okay, so sometimes you can get rationals that don't have a restriction, but it's rare. It typically will happen when you have an asymptote that is a slanted or an oblique asymptote. There's a slope to your asymptote. Here, as we look for our end behavior, x traveling to the left has y values that decrease and decrease and keep decreasing. So we're approaching the asymptote, but the value of the asymptote keeps decreasing as well, and so those y values will naturally drift towards negative infinity. So these two things match. As x goes to negative infinity, so does the y value. You could type this in your calculator to kind of get a perspective of this. Negative 1,000, well, negative 999. Negative 10,000 is very close to that amount. And so they just kind of gradually keep going together and together and together. And so that's just the scientific notation of the number that I put in. Basically the same thing. They're headed in the same directions. Then on the right hand side, as x goes to infinity, okay, the y values are also going to go into infinity. It's headed upwards. If I wanted to show you that on my calculator, that's pretty easy to do as well. So if I typed in 500, the y value I'm getting is basically 500. If I type in 5,000, the y value that I'm getting is basically 5,000. Add in another 0 with that, 50,000, and you basically get 50,000. So they trend together. They're going at the same direction, same rate, basically. And that's something you need to look out for when you graph these. End behavior, range, is all situational, depend on what we're seeing over here. Hopefully that helped and answered some questions on how to graph things that have an oblique asymptote. But if you guys have any questions, feel free to ask, and we'll see you guys in the next video. Thanks. Bye.